Afternoon, everyone. Welcome to Attacking SDN Infrastructure. Are we ready for the next gen networking? We are currently in Mandalay Bay, GH, with Cheng-Un Yoon and Seung-Soo Lee. Before we begin, I have a brief note. Please put your phone on vibrate. That's pretty cool. So without further ado, the presentation.
Hi, thank you so much for coming in. So we'll be talking about the security issues in SDN infrastructure today. And here we have a summary of content. And before we move on, we would like to introduce ourselves very quickly. My name is Chang-Hun, and this is Seung-Soo. We're both PhD students at KAIST, and we're currently working with Professor Seung-Won Shin. He is leading a network and system security laboratory at KAIST. We've been working on various SDN security-related projects, and today we would like to share some of the findings. So a network device that we're familiar with today can be broken down into two abstraction layers, the control plane and the data plane. While the data plane is a just fast packet processing layer, the control plane deals with various routing protocols and maintains forwarding states. So the control plane has become very complicated, and it has led networks to be unstable and difficult to manage. And also these devices are closed and proprietary, and it has been a barrier to innovation. So this software-defined networking that separates the control plane from the data plane was proposed. So here we have an example SDN architecture, and as you can see, the control plane is decoupled from the network devices. And the SDN controller manages the entire network in a centralized manner. So SDN controllers can easily provide and maintain a global network view. And also these SDN controllers implement northbound APIs, so anyone can easily develop useful and innovative network services or functions by simply writing SDN applications. And another advantage of SDN is that it is possible to build a network with commodity servers and switches, so the cost can be significantly reduced. So here we have a very simple network topology with one SDN switch and two network hosts. And the switch is connected to an SDN controller. If in this network, if host A wants to try to talk to host B, the switch doesn't know what to do with the packet received from host A because it doesn't have its own control plane anymore. So it queries the controller, and the L2 forwarding application running on top of the controller instructs the switch to forward all the packets from host A to host B by installing this flow rule. So once this flow rule is installed, host A can talk to host B. So that was a quick introduction on SDN. And today we'll be introducing some attack vectors that could affect SDN infrastructure, and particularly we would like to focus on data centers today. Oops. So the modern data centers deal with a lot of virtual machines, and accordingly the east-west traffic that travels within the data center has become dominant. So the data centers have recently started employing this leaf spine design that reduces the latency and the possible bottlenecks caused by east-west traffic. But even with this new design, there still remains other challenges to be solved. So the data center should be able to deal with frequent VM migrations and also a large number of links. And it is still expensive to scale and maintain the data centers. So this software-defined data center, or SDDC, is rapidly gaining attention as it can solve the challenges that I just mentioned. The SDDC can reduce the complexity by leveraging the global network view and network programmability offered by SDN, and it is also possible to reduce the capital expenditure by building and scaling the data center with commodity servers and switches, and also it is possible to reduce the operational costs by centralizing and automating a lot of management tasks. So as you can see in this figure, we've constructed a 3-node SDN controller cluster to construct a highly available SDDC control plane that can deal with a large number of network devices and hosts. And this control plane is also scalable because it is always possible to spawn more virtual machines to host more controller nodes if needed. So what are the attack vectors that could affect the SDDC infrastructure? On our list, we have misconfiguration and malware and insider attacks. So we'll talk about each one of them in the next few slides. And the SDN controllers that we consider in this talk are Open Network Operating System and Open Daylight. They're cutting-edge distributed network operating systems, and they also provide base design for commercial SDN controller products. For example, Brocade's SDN controller is based on Open Daylight. And they're also similar in that they both are Maven projects and they run on Karaf OSGI container. So the first attack vector that we would like to introduce to you today is misconfiguration. So ONOS and Open Daylight both implement various interfaces for management purpose. And if an attacker can gain access to any one of these interfaces, the attacker can freely manipulate the entire SDDC network. And regarding this attack vector, ONOS, the Open Daylight community has released a security guideline, and the possible mitigation would be changing default credentials and properly configuring the network. Also, ONOS and Open Daylight are prone to malware, and the infection can take place during the project build and also when they're running. So how is it possible to compromise SDN controllers at build time? So as mentioned earlier, ONOS and Open Daylight are both open source Maven projects. So the users would typically download the project source from a trusted source code repository, and then they would build it using Maven. And during the build, all the required libraries are automatically downloaded from a trusted Maven repository, and then the resulting package can be deployed to the actual control plane. But if ONOS or Open Daylight was built in an insecure environment, malware can be injected to the deployable package. For example, if there was a network attack against the build environment during the project build, malicious library could have been pulled from untrusted repositories and injected to the deployable package. And if this infected package is deployed, this may put the entire data center at risk. And another attack vector is malicious SDN applications. ONOS and Open Daylight both support hot deployment of SDN applications, so the network administrators and operators can easily install SDN applications using CLI, GUI, or REST API. So to make them download and install malicious SDN applications, social engineering attacks can be used. And once this malicious application is installed, the application can manipulate the behavior of the control plane and the entire network. And lastly, the SDDC control plane is also prone to insider attacks launched by malicious tenants. The malicious tenants may generate massive network flows to saturate the control plane, and also they may send out crafted packets to manipulate the global network view maintained by the controller. The papers regarding these attacks have been published, so please take a look at their papers for more details. So now we'll demonstrate two attack scenarios that breaks the SDDC infrastructure. And in the first attack scenario, we assume that the victim has built ONOS in an insecure environment. And we use a ROG Maven repository to inject malicious library into the deployment package. Once this infected package is deployed, the malicious code will be executed, and the attacker will get a remote access to each controller host machine. And then we'll try to inject an arbitrary ONOS node to the control plane. So let's take a look at the video clip. So on the left, we have victim's ONOS GUI, and on the top right, we have victim's build host, and on the bottom right, we have attacker host. So now we're currently downloading ONOS source, and then we're now building the project source with Maven. And once it's built, we're going to create an ONOS package that is actually deployable to the control plane. And now we're deploying the package to 3 different virtual machines. And once deployed and the ONUS cluster has started, as you can see on the left, we have a 3-node ONUS cluster formed, and on the attacker host, we have a reverse shell connected back to the attacker. And as you can see on the attacker host, it is possible to access and modify all the ONUS configurations, including the credentials to access CLI and GUI, and also REST API. And also, it is possible to modify the cluster configurations. So we're going to manipulate the cluster configurations to inject an unauthorized ONUS node to the cluster. So once the cluster restarts, as you can see, we have a 4-node ONUS cluster, including one unauthorized node, and the attacker can easily access the control plane and manipulate the entire SDDC network with this unauthorized node. And from now on, Seung-Soo will introduce you another attack scenario that involves malicious SDN applications.
Okay, thanks, Chang-un. I am Seung-Soo, and I will take over from here. So this is another attack scenario that demonstrates the threat of malicious SDN application. So in this case, we assume that the network operator has been fooled by social engineering attack and downloaded a malicious SDN application. So once the application is installed to the SDN controller cluster, the application stealthily degrades the overall network performance by abusing a weakness of a particular switch firmware. So let's take a look at the video clip. So as a proof of concept, we use a simple test topology that consists of 1 HP switch device and 2 network hosts. And on the left, we have an OpenDLI controller console, and on the right, we have one of the network hosts for performance measurement. And also here, we have a malicious SDN application and the other bundles running inside the controller. So when the switch is connected to the controller on the network host, we perform the ping test to show the network performance before installing the malicious SDN application. So as you can see that the switch forwards the traffic by looking at its IP addresses. So except for the first packet, it took about 0.3 milliseconds to forward each packet. So and next we installed and then started the malicious SDN application, and this malicious SDN application has replaced the existing IP matching flow rules with the MAC matching flow rules. So as a result, you can see on the right, the ping latency is increased to about 0.7 milliseconds, which is twice as worse. So the demo of those 2 different attack scenarios involve the 4 different vulnerabilities. So from now on, we would like to go over each one in the next few slides. And also, we have documented many other vulnerabilities. So will be available on sdnsecurity.org. So please visit for more information. The first problem we'd like to point out is that there is no system integrity protection for SDN controllers. So as demonstrated, the malicious libraries can be injected in the build process, and the source code of SDN controller could be manipulated before building. But currently, since there is no such mechanism to detect a loss of system integrity, the network operator might directly deploy the compromised SDN controller to the network. So the code signing or other integrity protection mechanisms such as checksum could be possible solutions to this problem. The second problem of SDN controllers is that there is no authentication of SDN controller cluster nodes. So as demonstrated, we were able to inject an arbitrary ONUS node to the ONUS cluster by simply manipulating the configuration file. This is a serious threat because the arbitrary on-off node can completely take over the control of the entire control plane and the network. Obviously, it is okay if the cluster node communicate using a dedicated or secure channel, but this could add a significant complexity if the cluster nodes are geographically separated, as shown in this software-defined WAN example. So to solve this problem, the PKI authentication could be one of the possible defenses. The third problem is that there is no access control of SDN applications. In the current SDN controller, the applications are granted very powerful authority, even though they are just applications running on an operating system. So those applications, including even malicious ones, can access the core of the controller and freely manipulate the network behavior as we demonstrated. In addition, the applications can access the host machine and execute the system commands. But even if the network operator deployed the malicious SDN application to the SDN controller, the controller should be able to restrict the malicious, the application's behavior that is potentially dangerous. So to limit the authority of those applications, the police-based access control mechanisms could be useful, like the one used in Android system. Lastly, to degrade the network performance, it is possible to abuse a particular switch firmware that affects the packet matching strategy. Currently, the most SDN switch devices implement both hardware-based and software-based flow tables. So if a packet is matched by looking up the software table, it incurs a significant overhead than hardware flow table. So such packet matching strategy might vary depending on the vendor and firmware version. So in the case of HP 3800 switch devices used in our demonstration, the flow rules with specific MAC addresses are handled in the software table as shown in this chart. So in our demonstration to abuse this strategy, we replace the existing IP matching flow rules with the MAC matching flow rule like this. As a result, as shown in this graph, the packet forwarding latency doubled after the attack. But this attack does not affect the network connectivity. It is difficult for the network operator to figure out the true cause. So one possible defense mechanism to mitigate such an attack would be detecting and arbitrating flow rule conflicts. Finally, we would like to introduce you two of the ongoing SDN security projects. So first one is Project Delta, that is an SDN security evaluation framework pushed forward by Open Networking Foundation. So the purpose of this framework is to automatically replay the known attack cases against SDN element so that we could measure the security status of each element, and also to assist in uncovering an unknown security problem within an SDN deployment by performing first test. So another project is Security Mode On-Us, and it is a security extension to On-Us. So in order to protect the core of On-Us and the network from untrusted SDN applications, this extension enforces the security polish to each SDN application. So just like those mobile application security framework. So it detects and blocks any violation. So the other vulnerability we could not cover in this talk will be available on this website called sdnsecurity.org. And also we provide the details on our security projects here. So please visit if you are interested. In conclusion, so our answer to the question, are we ready for the next gen networking, is unfortunately no, because we believe there are still a lot to be done in a security point of view. So your urgent attention and contributions are needed. Thank you for listening. Yeah. Any question?
out. How does this affect the number of components and how many of the IoTs are being deployed as software-defined networks or just insecure components underneath regular networks? Or I presume it complicates this problem.
The question was, as the IoT deploys out, how does this complicate the problem? I mean, it's more insecure components underneath any kind of network, whether it's software defined or any. But does it particularly add problems to the issues you've talked about here?
Yes. So the vulnerabilities that I introduced you today basically are the software components, and they're very fundamental components that could be applied to any software-defined environment. And of course, IoT is also part of that. So if that IoT environment has adopted SDN using the SDN components that we introduced today, the security issues will arise as well as our demonstrate as well just like we demonstrated. Any other questions? Okay. Thank you so much for listening.